All right, let's go through an example. When you do statistical inference, it's one thing to really kind of learn the steps, but to really understand it, it's always good to go through a few calculations and really tie it to an example. So let's look at religious affiliation. This is the same example we were working with earlier. This is our basic table of counts for religious affiliation among young people in the United States. This is based on a real set of data. So we can see we have 247 Protestants, 132 Catholics, and 139 young people who don't have any religious affiliation. And you can see we have K equals 3 categories, and the sample size is 518. Our armchair religious studies scholar, he's claiming in his ivory tower that there are 60% Protestants, 35% Catholics, and 5% young people who don't have religious affiliation. Right? You can think of this as really a probability distribution because he's talking about proportions. So the probability of being Protestant is 0.6, the probability of being Catholic is 0.35, and the probability of having no religious affiliation is 0.05. For using the chi-square test statistic, these proportions should equal 1, and we use lowercase a to refer to these claimed proportions in the population. Remember, we don't observe the population, so this person's just making claims about them. Then we have this random sample from the population, and we have these observed counts. Right? These observed counts, we use capital O. So the observed counts are simply those from the frequency table. Right? And then we have the expected counts, which we calculated earlier. The expected counts are simply the sample size, which is 518, times these different proportions. That will give us an idea of, with a sample this size, and if this claimed proportion is true in the population by this religious studies scholar, what would this distribution look like? Well, you'd have roughly 311 Protestants, roughly 181 Catholics, and roughly 26 young people who don't have religious affiliation. And the crux, the key part of the chi-square one-way goodness of fit test is to say these observed counts and these expected counts, how different are they? The more different they are, right, the larger our chi-square test statistic, and the more inconsistent our data, those observed counts are, with our null hypothesis, right? With this set of values claimed to exist in the population in terms of these proportions by the religious studies scholar. So let's go through a couple steps. Steps 1 and 2, at this point we've already conducted the preliminary tests, the preliminary sort of steps of just checking to make sure it's a random sample and all that, because the expected cell counts are each greater than 5. So we can move on to steps 1 and 2. Right? We will conduct a two-sided chi-square test for this course, and in general, you will only really see two-sided chi-square tests, and we're going to have the following hypotheses. The null is simply that the proportions in the population for each of the categories are indexed from I equals 1 to K, so we have Protestants, Catholics, and nuns. Those are 1, 2, 3. The null is simply that those sort of claimed values by this religious study scholar equal the proportions in the population. The alternative is simply that at least one of these proportions, P1, P2, or P3 in the population, it's not equal to the claimed proportion. Right? There's something off here. That's the alternative. And for sort of by convention, we will set alpha to 0.05. And this will affect our critical value as well as our cutoff for what counts as a statistically significant probability value. For step 3, we will calculate the test statistic. Recall that the chi-square test statistic is simply the expected minus the observed counts squared divided by the expected cell counts for each of the categories, and then you add them up, right? So you add, and that's all the sigma's operator is telling you. That capital sigma is saying to add up what is after that capital sigma for each of I equal 1 to K, right? So we can calculate this as follows. Right? We have 3 different terms. Okay? That's because we have 3 different categories. We have K equals 3. So for I equals 1, right, we have these expected observed counts. We take 310.8 minus 247, square that, and divide by the expected cell counts for that first category. For the second category, we have the expected cell counts are roughly 181. We subtract out the observed cell counts, square it so it's positive, and divide by the expected cell counts for category 2. Finally, for K equals 3, for that last category of nuns, we take the expected cell counts of 26, subtract out the observed cell counts of 139, square it so it's positive, and divide by the expected cell counts of roughly 26. When you add up these 3 different terms, we get this chi-square test statistic of a little over 520. One way to think about the chi-squared test statistic is it's kind of like a standardized value. Right? We're standardizing each sort of difference between the expected and observed counts by the expected cell counts. So we're kind of it's a standardized value that kind of gives us the consistency or inconsistency between our observed and expected cell counts. Right? If those values of E and O for each category, if those are large, those squared values are going to be pretty large. Right? And the larger those differences, right? The greater the difference between the expected and observed counts, that larger that value of the chi-squared test statistic, suggesting inconsistency between our claimed proportions and our actual observed counts. So once we've calculated the chi-squared test statistic, we can compare it with a critical value. So the idea behind it is that if the chi-squared test statistic is greater than or equal to the critical value, then we reject the null that the population proportions are equal to the claimed proportions in the population. So we've set alpha to 0.05. We have 3 categories, so our degrees of freedom is 2. And using that, our critical value, our benchmark by which we can judge our chi-squared test statistic is 6. The idea being that if we observe a chi-squared test statistic greater than or equal to 6, then we can reject the null. Well, in our case, okay, the chi-squared test statistic is very large. So it's much larger than the value of 6, so we can reject the null. We can also use the p-value. The idea behind the p-value is that it gives us the probability of observing some chi-squared test statistic greater than or equal to the one we've actually observed. And again, if our p-value is equal to or less than alpha, we reject the null hypothesis. In this example, you can see our chi-squared test statistic is way over to the right. It's very large. That just reflects the fact that our expected observed counts, they're really quite different from each other. And so the p-value, the probability of obtaining a chi-squared test statistic as or more extreme than the one we observed, under the assumption that the null is true, that the observed counts are roughly equivalent to the expected cell counts, or to put it another way, the idea being that the population proportions equal the claimed values in the population. It's very small. The probabilities, it's very unlikely to have obtained the data we have if that religious studies scholar is correct, if that religious studies scholar is truly correct in saying that the distribution is as he has described. Right? So we reject the null. In both of these cases, we reject the null. So focusing on young people aged 18 to 35 who are Protestants, Catholics, or have no affiliation, we're going to reject the claim that 60% are Protestant, 35% are Catholic, and 5% have no religious affiliation. In these findings, we can say are statistically significant at the alpha equals 0.05 level. If you look at the expected and observed counts, you will see that these findings suggest that young people are much less religious than this scholar is claiming. Right? You can see that the expected cell counts for those without a religious affiliation is much smaller than the actual observed counts.